This video will start to talk about gas laws. We're going to start with the combined gas law, which actually incorporates a bunch of other smaller ones. And I'll kind of explain how you can use this one to address a lot of different situations. So the combined gas law has three variables, which we'll get to in just a second: temperature, volume, and pressure. So this slide just tells you a little bit about the relationship between temperature and volume. So we're just looking here as if pressure is constant. When temperature increases, volume increases. Okay, so if you think about that, if temperature decreases, volume will decrease. So if you've ever had a balloon and you tie it so that no air can go in or out, if you take it outside on a cold day, you will see it shrink. If you put it in the freezer, you will see it shrink, because when temperature goes down, so does volume. That is what we call a direct relationship. It means that when one thing happens, the other variable is the same thing. So if volume doubles, then temperature doubles. If volume halves, then temperature halves, okay? They have the exact same relationship. So this little formula is going to come into play in just a second. We're just using K as a generic constant here, okay? Just meaning that if you increase volume, you also have to increase temperature. If you decrease volume, you also have to decrease temperature, because that K, whatever it happens to be, this isn't a constant that's like known for every gas or anything like that, but whatever it has to be, it has to stay the same. If you change one, you have to change the other. So now let's take a look at pressure and volume. So in this situation, we're assuming temperature is constant. Pressure and volume have an inverse relationship. So whatever happens to one of them, the opposite happens to the other one. So if pressure doubles, volume halves. If pressure goes down, volume goes up, okay? So same thing here, we have this K, just generic constant. Pressure times volume is going to be a constant. And our last relationship is pressure and temperature. We are assuming volume is constant here. They are a direct relationship. So volume is constant, and when pressure goes up, temperature goes up. Pressure goes down, temperature goes down, just like volume and temperature. So the combined gas law is putting all three of these together. It's combining them. So the combined gas law is this. Now, you generally will not see N's in the combined gas law. N stands for moles. You generally don't see that, and you don't need it. I'm going to keep it here, and I'll show you what to do when you don't need something. Usually you wouldn't need moles, but just in case, here it is. So P1 is your starting pressure. The 1 just means starting. So P1 is your starting pressure. And that can take 3 different units. It can be atmospheres, which we write ATM. It can be something called mmHg, which in times long ago they would refer to as torr. If you see that, it's the same thing. And you can also use kilopascals, or kPa. Volume is V, so V1 is our starting volume. And our units are going to be either milliliters or liters. Most of the time, liters, because we're talking about gases, so it's big. N1 is starting moles. And the unit for that is just moles. And T1 is starting temperature. And that must be in Kelvin. If you do not have your temperatures in Kelvin, these gas laws do not work. Neither combined or the ideal, which we'll learn about in the next video. So on the other side, we have the same exact variables, but with a 2. That means it's the final pressure, final volume, final moles, final temp. So this is going to be your final pressure, and it's the same units. So whatever units P1 is in, it has to be the same for P2. So if it's kPa on P1, it has to be kPa for P2. So as long as they're both the same, there's no conversions necessary here. And then same for volume. This is going to be your final volume, and it's going to have the same units. And then we have final moles, same units, and final temp must be in Kelvin. So there's our combined gas law. You'll see that on this slide I talk about it as the before and after gas law. Our other gas law that we'll learn about, the ideal gas law, is just at a point in time. Something is happening to your gas. Okay, there's some kind of thing where you have some values before, some values after, and you're comparing the two. So let's take a look at one of these problems. So the first thing you should do is go through, label all of your numbers or all of your givens with a variable. So if you're not sure what the variable should be, look here. That's why I listed the units here. So if you look at the units, like if you're given, so this says consider 0.5 liters of gas. It doesn't say, is that pressure, volume, temperature? So if you go up here and you're not sure, you find the one where I wrote liters and you're like, oh, that's volume. So that's going to be V. So here, I'm going to call this one V1 because it's the first volume. And then we have 50 degrees Celsius. Now we just said you can never have a temperature in anything other than Kelvin. So what I do right away is cross this out and write a new temperature. So remember, for Kelvin, we do degrees Celsius plus 273. So here I'm just going to take that 50, add 273 to it. And so right away, I'm going to change this to Kelvin. Then I will underline it and label it as a temperature, T1. Okay, because you have to use your temperature in Kelvin in these gas laws. Then we have a pressure of 200 mmHg. That's P1. So now we're going to have our new volume, V2. We have a new temperature, but it's actually the same temperature, 323 Kelvin, T2. And what will the new pressure be? So let's take a look at our combined gas law. There is no mention of moles in this problem at all. If there is no mention of something, any of these variables, if there was no mention of pressure, we could do the same thing. So we can just get rid of moles. It's not going to factor into our problem because it's not there. We assume that moles are kept constant. Everything else is mentioned in the problem. However, if you look closely at our temperatures, temperature kept constant. So 323 and 323. If something is kept constant, whether it's mentioned or not, that means you can get rid of it in this formula. So I can take away the temperatures. Now, if you didn't notice that and you put in 323 for T1 and then 323 for T2, it will just work out in the math. Okay, so you don't have to worry about it. If you don't catch that, it's fine. It will work out. But if you do catch it, it does make your math a lot easier because now we just have P1 V1 equals P2 V2. We plug those numbers in. Whoops. And when you solve for this, you get P2 is equal to 100 millimeters of mercury. And that makes sense. Oh, sorry, I forgot to divide by, so P2, that did not make sense, and that's why I needed to take another look. I forgot to divide by 0.1. So we do 100 divided by 0.1, and we get 1,000. Now that makes sense. Okay, so it's really important to always make sure you check to make sure things look like they make sense. So we would expect that if we are going from 0.5 volume to 0.1 volume, we are going to have an increase in pressure, because remember, the pressure and volume have an indirect relationship. So we go from 0.5 to 0.1, that's lowering the volume. That means we're going to increase the pressure by the same magnitude. So we go from 200 to 1,000. It's important to keep those in mind, because as you just saw, when I said that makes sense, and then I looked again and I was like, oh, that's 100. I must have missed something up here. And I did. So go back and check and make sure your ratios always make sense and you're not just doing the math blindly. So let's take a look at another example. And here we have 2 liters as our volume, 0.8 as our pressure, and then this is in degrees Celsius, so we're immediately going to turn it into 298 Kelvin for our temperature one. To what temperature, so that's going to be T2 in Celsius, and I'll tell you what to do about that in just a second, should the gas be changed to reduce the pressure to 0.2? So this is another example of a way you might be able to get rid of some variables. Okay, so let's go to our combined gas law. There's no mention of moles, so we can get rid of moles again, and you will often be getting rid of moles in a combined problem. And then we do have a mention of a volume, but then it's not mentioned again. So that's another way the problem will tell you that volume is constant. Okay, so here, because it only says 2 liters of oxygen gas and then it doesn't tell you that the volume changes, that means you assume it doesn't change. Another way we can see that is this word rigid. It just means that it can't change volume. Okay, but if you didn't know that word, that's okay, because we don't have another volume. So we can get rid of the volumes. So now we have P1 over T1 equals P2 over T2. So I am going to solve for T2 because that's what I'm looking for. And I think the easiest way to do that is to cross multiply. So if you do P1 times T2 equals T1 times P2, it makes it all in a straight line. It just makes it a lot easier to work with. So P1, T2, T1, P2, and we are looking for this one. So I'll divide by P1 on both sides. So now I have my nice, easy formula where I can just plug things in. So our temperature is 298, our P2 is 0.2, and our P1 is 0.8. So when we do out that math, we get 74.5 Kelvin. So let's see if that makes sense to us, okay? The pressure went down. So what would we expect the temperature to do? We would expect the temperature to also go down. Remember, they have a direct relationship. So the pressure goes down, the temperature goes down. So we do have that going on here. We do have one more thing to do here. This question specifies that it wants the temperature in Celsius. You cannot use Celsius temperatures in the gas laws. The ratios do not work. So you do still, even if the question says Celsius, they try to trip you up like that sometimes. You do still need to convert to Kelvin, use Kelvin in the formula, and then convert back to Celsius at the end. So what you would do here to get to Celsius is just subtract 273. And that would be your new temperature in Celsius. So that's it for the combined gas law. And you can do any number of combinations with crossing out the variables here.